It's on live. Alloy polymers, alloy collections furniture customer மாதவத்தை பார்த்துருக்கேன். இன்னும் சிஸ்டம் மேட்ரிக்ஸ் இது குருவாச்சு. இது ரெண்டும் ஒன்றா முடிச்சிடலாமா? இல்லைன்னா நாளைக்கு வந்து முடிச்சுட்டு சாயந்தரம் நாளைக்கு நானும் ஒரு கஷ்டம் 2 வருஷமா பார்த்துருக்கேன். எந்த கஷ்டம்? கஸ்டமரோட விசிட் பண்ணிருக்கேன். எந்த ஏரியா? நான் வந்து சம்பத்தூர் வந்து நேராக மகேந்திர எங்கே போறியா? ஐடியா மகேந்திர சிட்டினா சாங்கா போறியா? Good evening, sir. Pradeep, sir.
Hey, good evening. How are you?
Yeah, doing good, sir. And how now my voice is okay?
Voice is good. I can hear a little, little hum. I don't know if it's from you or from me or from where.
Might be the air conditioning system compressor sound should be there. I think so, sir.
There's a little hum.
Yeah, should be. I think the compressor might be the sound, a humming sound. The air conditioning system compressor.
Your air conditioner?
Yeah, my air conditioner. It's ceiling based.
I think you can switch it off, Sarvanan. Hi, good afternoon.
Yeah,
Pradeep.
because hi Rashmi, how are you?
I'm fine. How are you?
Very good. So I'm just saying, if it's not a problem, maybe you should turn off the.
Yeah, it's done. Still you are getting the sound?
Yeah, I'm trying to see. I have no problem. It's just that it was not there last time. So
yeah, but now I had switched off that, but still you are
here.
So
then it is not because of your AC.
Oh, okay.
Then it is something else. So Rashmi, can you hear this little hum?
I was hearing it earlier. I think.
But
yeah, I can hear it.
Yeah, the hum is there. I don't know from where and why it is there, but it'll be it'll be like this throughout the presentation then. Okay, so Rashmi, I just want to know that am I logged in okay? Because I didn't know my link that you have sent is for participant or for panelists, but I should be able to share my screen, right?
Yeah, just share it so we'll know whether you're able to share your screen or
Okay,
not.
so I will share it now.
To get clarified, you are on the panel list, sir. So you will be.
Yeah, it's okay, it's okay. So I'm just checking. So
Yes.
Rashmi, just let me know if you know you hear my voice all right and you see the screen all right.
Yeah, both.
No, you should do a slideshow.
Okay, just one sec. Let me get rid of the guides and let's run a slideshow. Is it okay?
Yeah. Yeah, it's clear, sir.
Okay, that's fine. Voice is good. This is good. So I guess everything is good.
Yeah. We got a good number of registrations. We expect the same kind of people also getting in connected today. We hope for the best.
Sorry, say it again.
We got a good number of registrations yesterday. Till date, there is good number of registrations.
Oh, that's good. You see what happens in this industry, as more and more people get to know you, it spreads. So there's no harm if more people join and, you know, they get to know you more and more.
Absolutely, sir. You are right.
Okay,
I
so
think that hum is still coming. I don't
it's
know.
very bad, actually. It was not there last time. That's very surprising, actually. Now, is it, I'm just, you know, going to see, is it by any chance from me? Can I do something with my mic? Is it my mic? But it's the same computer as last time. I'm a little surprised if it is so. Why should it be there?
Recording mode is so the blinking button touch take it, sir. Line is at the humming video. What can you do?
Rashmi, can you hear me?
Yes, sir. You're audible, sir.
Yeah. So is Prashant going first or I'm going first?
Ma'am, ma'am, you're on mute.
Can't hear you, Rashmi.
I'll just unmute. Yeah, can you hear me now?
Yes.
Yeah, Prashant is going first and then it's your turn.
Okay, that's fine.
Ma'am, shall I give a call to Varagi, sir?
Yeah, you can call him, but it's a bit early right now, I think.
Just 5 minutes or 10 minutes more.
Yeah, at least we can check his video audio.
Yeah, ma'am.
He's joined.
Yeah.
Hi, good afternoon. How are you?
Good afternoon. Good afternoon, Pradeep.
Hey, good afternoon, Prashant. How are you?
I'm fine.
Good afternoon, Vairagi sir.
Good afternoon.
I'm stop sharing my screen. Can you share your screen so that we know everything's on track?
True. Okay, I'll do that. Hmm, I'm unable to see my screen itself. I mean, can you see this?
Um,
1 second.
Yeah, we can see your system, sir.
yeah,
Okay.
actually, you'll have to close all other files. Only open up your presentation.
Can you see the presentation now?
Yes,
Yeah,
sir.
we can. You'll have to do a slideshow.
Okay. I can do page. This is PDF file. I can do page up and down also.
Yeah, but you'll have to do it on a slideshow.
If you press Control L, you'll go to slideshow.
Okay.
Good afternoon, Prashant. Good afternoon,
Yeah.
Shekhar.
Good afternoon,
Good
Shekhar.
afternoon.
Yeah.
Hi, good
Fine.
afternoon.
Good afternoon, sir.
But I am unable to see myself. That is okay?
Why?
Because
You want to? It's okay.
You can see the you can see
We
from
can
the
see you.
broadcast, right?
Yeah, I can see my presentation, but I'm unable to see any one of you. You know.
That's
Why?
okay. You're not missing anything.
Okay, fine. But you are you able to see me, or you're also not able to see me?
No, we can see your presentation, not you, and that's also
That's okay. That's good enough.
If you can switch on your video, we will be able to see you.
Yeah.
Yeah, I think you must have
And
stopped
how
your video.
when Alexi was presenting in the corner, he was also visible, and the slides were also visible. You know, how was that?
That's how it is. It is depends on how you are set up yourself. If you exit
Yeah, you do a slide gallery. So on the top right hand side, there will be view, a button on the right hand side which says view.
One
So
second.
if you click on the view, then it will
Okay.
be side by side speaker or side by side gallery. So if you select side by side gallery, then you will be able to see all of us.
1 second.
Hi, Alexi, how are you?
Hello, Asmi. Super fine, and you?
Yeah,
Hello,
good
Zeka.
to see you.
Alex. First time I'm seeing you with a mask.
Yes, we have to. We have to.
Rashmi, what you said? What to do?
In India, we are doing.
Right hand side top, there is this button view. So you click on
Correct.
view.
Yeah, I did that.
And you make a selection.
Selection after pressing.
You click on it and it will give you standard side by side speaker, side by side gallery. So if you select side by side gallery, you will be able to see yourself as well as all of us. There you see us.
I don't see any such options after pressing that view.
Yeah, it's there on your screen. We can see it.
Okay, where it is? It is recording your. Okay, it is. 1 second.
Right hand side top corner.
Right hand side top corner is basically preview, pause share, stop share,
The view. Click
view.
on this.
I did that.
Video.
Then after
Then
that,
you get options.
I could not see any of the options.
So if you stop sharing, you will see the options.
Okay.
Right now you're sharing your screen.
Okay, so I have to stop sharing. Fine.
Yeah.
Fine. Yeah. So after pressing view, Speaker view, gallery view. Fine. I have to
Yeah.
go to gallery view. I'm learning from you. Huh?
It's like everyone learns these days, even kids are good at this. We all are learning from the next generation.
Okay. So now it is view that I have done it. Okay. So now when I share, now I have to do the sharing, right?
Yeah.
Okay. Fine. Okay.
Yes. You have to share your screen.
Yes. But then again, it is coming only that presentation part, you know. Can you see that?
I can see it, but I don't think it makes much of a difference. So we will take your pictures for you.
Fine. Fine. It's not required. I will start sharing my presentation.
But you'll
only.
have to switch on your video.
Okay, I have done that.
You are not done.
No, we
No,
can't
no,
see
no,
you.
no. I have not done that. I have not done it. Fine.
Yeah.
Let me do that again. Yes. Now.
Now we can see you. So now you will be visible when you start your presentation.
Okay. Fine. Okay. It is already 3 o'clock. I'm in 2 minutes.
Yeah. So I think you'll have to stop sharing and I'll have to start sharing.
Okay, I will do that. Okay. Fine. Fine. Okay. Thanks.
Hello. So my screen is visible?
Yes, ma'am.
Yes, yes.
I think we already have around 24 participants, so we can start.
Incidentally, Prashant and Chaudhary, I think this is the time we had something like 800 people showed interest to participate. Okay. So this is the 7th series, but we normally used to hit around 350, 400. This time, speaker being so good, I think we had 800 plus interest. I'm sure people will be joining. Good. Yes, Rashmi, you can start.
Yeah. So good morning, good afternoon, good evening to all the participants and all the panel members. First of all, wishing everyone a very, very happy new year. 2021 has started and I think business has also started once again. So incidentally, I was discussing with Pradeep and he reminded me, today is the 21st day of the 21st year of the 21st century. So hope that it turns out to be lucky for all of us sitting over here. So in case my screen is visible, I'll start. We have participants and presenters from different regions of the globe, from within India and from different locations across different continents. So welcome to all the participants to the Plastics Flame Retardancy Learning Series number 7. We will be discussing the design perspective in flame retardant components. And this is organized by Formulated Polymers Limited and Eurostar Engineering Plastics, which is now Ascent Performance Materials. Basically, the presentation is for all practicing professionals in electrical electronics industry, as well as automotive, electrical vehicles. We are looking at an entire span of industry, the new areas which are growing. So all those people who are associated with design, selection of materials, processing of these flame retardant materials, testing and various applications and the new applications, especially in robotics as well as artificial intelligence. Oh, I'm not able to change my screen. Yeah, just. So my name is Rashmi Bhardwaj. I'm Vice President Development with Formulated Polymers Limited. The webinar will be for around 45 minutes, 40 minutes of the presentation and around 10 minutes of question answer. So request all the participants to post your questions in the QA box below and not in the chat box. This webinar is more practical and not so much theory based, because all of us are actually hands-on with FR components, FR materials, various applications. Just to do a quick recap, we have done 6 series as of now on flame retardancy. First series was on history, need, ISO classification of FR chemistry. Series 2 was on FR mechanism and selection criteria. Series 3, testing of FR characteristics, part 1 and part 2 was series 4. Series 5 was on how to read various standards, and we had presenters from UL and VDE. Then series 6, Alexi and Satish gave a presentation on processing of FR compounds. Then in future, we have series 8, 9, 10, and we will have a few more series also. The environmental impact of ROHS REACH compliances will be the next series. And then we'll be looking into post-care, pad printing, laser marking, etc. 3D. Then series 10 will be on cross-link polymer FR systems, and series 11 on applications of FR compounds. So basically, we'll be closing with the future trends. And in case we feel that there is a need or there is a request from all the participants, we will go in for a few more series based upon the requirements. All the series which we have done till date, they are available on the YouTube. We have a YouTube link. Except for a couple of them, like in case of UL and VDE, it'll be available on the their websites. So I think those presentations we have not shared, but all our presentations we have shared with the concerned participants. So a flame retardant mechanism, we covered up various halogenated nitrogen, organic phosphorus, inorganic phosphorus, metal oxides, boron and zinc, silica compounds, and then we did a couple of series on testing. So we went into detail regarding the UL94 and the glow wire flammability tests, which are one of the most critical tests. We also covered up LOI, smoke density, CTI, then the hot wire ignition, arc ignition testing, arc resistance, also the long-term property evaluations for as per the UL746B. This was a series where we discussed on standards, how to read UL and VD. So I think in continuation, we had on processing, where Satish from Schneider and Alexi from Eurostar Engineering Plastics had given us a detailed overview. What are the care and guidelines which we have to take during processing of FR compounds? So some of the industry professionals have already presented, some are have agreed to present. So we would request the industry experts, the professionals, to come forward and present future learning programs. It's a sharing platform, and we would request everyone to share the knowledge which they have gained, so that we can take this forward and have it much easier for the next generation who are working on similar products and are looking for better performances. So since Eurostar Europe and FPL Asia specialize in compounds of engineering polymers, most of the examples would be based upon polyamides, ABS, polypropylene, HIPS, MPPO, polycarbonates, and certain blends of polycarbonates. So now coming to the present series, we have Pradeep Chaudhary, who's the principal consultant, product development solutions, Design Plus, and Prashant Vairagi, Senior DGM Plastics Technology with Schneider Electric India Private Limited. I'll be giving a brief introduction about both presenters. But before we start talking about Formulated Polymers Limited, we have the Starflame grades, we have the Form Poly grades. Both are available in reinforced and unreinforced ranges. And we have various properties like high impact, various tight tolerances, etc. Complete UL yellow cards in all colors. We have CTI values which go up to 600 volts, RTI values of 120, which can go up to 150 degrees centigrade, various compliances, laser markable grades. So this is a slide which we have shown in all our presentations, just a summary of the FR systems, where we have a very high level of competency. Now coming to our presenters, Mr. Prashant B. Vairagi, Senior DGM, Plastics Technology, Switchgear Design and Development Center, Powai Campus, Mumbai. His education is, he's a plastics engineer and a diploma in electrical insulation technology. He's a faculty for STDC switchgear R&D on plastics and rubber materials, plastics application development specialist with a vast experience. It's 35 years where he has worked across all plastics product design, processing, testing, injection mold design for both thermoplastics as well as thermosets. He's a certified ATM for CMMI level 3. Incidentally, he's an author also for plastic design guidelines for switchgear applications with 7 modules, and his module 1 and 2 is certified from SAVE International. Formerly, he was working with L&T Switchgear Business R&D with expertise in insulating materials used in contactors, relays, starters, the entire range of electronic controllers. So today, design considerations when using FR materials in ES applications by injection molding and extrusion. This is what he'll be discussing, along with cost-effective designer tips and tricks to overcome challenges in miniaturization, which is very important in today's day and age. So welcome, Mr. Prashant B. Vairagi. The second presenter is Mr. Pradeep Chaudhary, Senior Consultant, Design Plus. He is basically an alumnus of NID, the National Institute of Design, done a integrated course equivalent to a master's in design. He has several patents and design registrations filed as a primary or jointly or transferred rights to his clients. His latest patent is filed to enable lightweight headgear to ensure high levels of purified air supply for various healthcare workers, sports, etc., high altitude deployments for N95 masks. In 2000, he received Innovators Award for Design with Engineered Materials in Electrical Applications. Started his career in 91 as an application development specialist in GE Plastics India. Worked in Holland also with GE Plastics. Then he translated a lot of good applications and headed the GEP Engineered Resins portfolio in year 2000 for 5 years. Presently, he's a product development solution specialist with Design Plus as well as Industry Development Network. So he also has a very wide experience of 28 years in product development and also has worked as advisor with various organizations. So in today's series, he'll be discussing the design perspective and advantage of CAD software tools for mold flow, finite element analysis, computational fluid dynamics, CAE simulation in various FR materials for the next generation electrical applications. So I'll be handing it over to Mr. Prashant B. Vairagi. I'm stopping sharing. Mr. Vairagi, please share your screen. Prashant.
Okay. Yeah. Okay, we will be talking about role of plastic materials, especially FR materials. Though all components may not be FR, but then concern is with respect to FR materials only. For electrical and electronic applications, we'll be considering briefly insulating materials because there are various kinds of materials that we'll be using. Functional requirements while we are selecting the material, what are the criteria, and product application and aesthetic, which is equally important. What are the different considerations that we have, in mind? First, nowadays, most important is the green switchgear. The best example of that is the LED lamps, which consumes the less material at the same time less electricity. Second criteria is miniaturization. reducing the
Prashant,
size
can
of the
you
product.
do a slideshow? Your screen is very small, coming very small.
Okay,
In
fine.
case you're, yeah.
1 second. Just hold on.
Just to Control L, and I think it should be done.
Fine, fine. Yeah, fine. Yes. Can you see now? Hello.
It's coming. Yeah, now. Yeah, now. Great.
Yeah, fine. Okay. So what we are talking about, the different criterias. In one of that is the miniaturization. You are basically reducing the size of the product. Moment you reduce the size of the product, obviously the material quantity will come down. Cost also will come down. The panels, that is switchboards and other areas where we are mounting these products, that also will require less space. Floor space will be less, but then unfortunately, whether we like it or not, all metal parts, that is conductive elements, that is copper, silver, because of the current density, their dimensions or thickness and other parts, that will not change. So moment anything has to be compromised is the plastic part, and moment plastic part gets reduced, it has to withstand high mechanical load, maybe short circuit conditions, or all those things will go severe. Even temperature severity for the smaller size will increase. So as far as plastics are concerned, the selection will become tough moment you reduce the size. Of course, that is for added advantage. The examples, as we know, mini circuit breakers and residual current devices and all, RCD and all, protection from point of view, we are looking for certain compliances like IEC, ROHS, WEEE, REACH, all those things are already covered by formulated series. Environmental aspects, that when we say environmental, the use of halogen and halogen material, red phosphorus material, based FR system, but then people may not take the call immediately based on that, because moment you select halogenated material price will be lower. However, there are certain things that we have to compromise. First, density will go up. What we use the material, or what we inject the material into the mold is by volume and not by weight. And when we buy the material, we buy by weight. So obviously one has to see that, if you are buying a cheaper material, how many components you can produce from a given bag. Okay, so, and obviously the other aspects like halogenated materials will have low CTI, its breakdown voltage value also will come down. Red phosphorus materials will give you limitation with respect to color. Either you can go for brick red color or black color. There will be you cannot go for any other colors. So all those things we have to consider while going from the environmental point of view, as well as your functional and price aspect is concerned. Efficiency, when we consider, we also consider the density of the material, because the product weight is also important, whether it can be colorable, because from the aesthetic point of view, certain components, outside component, you have to consider that aspect. Shrinkage, reduce shrinkage for controlling the warpage and all, and obviously flammability and UV resistance. Other criteria is basically UL94V0, whether we want 5EA, CTI, arc resistance, basically electrical properties and flammability characteristics that we consider. And from the modular design point of view, because as the product is becoming compact, it is better to go for modular design. It is good from the assembly point of view. Assembly is easy. It is less complicated. It needs relatively less accuracy. And in short, you should be able to make a product in your home. That is the concept that one has to keep into mind. And then functional integration. When you are doing, it should be easy to accommodate certain assembly aspects that we will be discussing. Cost and productivity, as I mentioned earlier, it is very important. And then one has to consider the freedom of design from the functional integration point of view, better mechanical strength and lower product weight, which I have already discussed. Now, insulating materials, as far as insulating materials are concerned, various materials that we use, thermoplastic, elastomers, thermoset composites. We also do consider alternates for metal, alternates for thermoset composites, and modified thermoset composite. So if I am not going to discuss much on the insulating materials, but then just to brief the various semi-crystalline materials that we use, that is nylons, PPS, PBT, that is all types of polyesters, polypropylene, polyoxymethylene, polyacetal, what we commonly know, amorphous material like PC, ABS, elastomers, that is thermoplastic elastomers I am talking about, polyurethane, EPDM, and alloys and blends like PP, EPDM, and polypropylene nylon 6. Those are also equally important. Thermoset material commonly phenol formaldehyde, melamine formaldehyde, polyester melamine, urea formaldehyde, trans-saturated polyester. Other form is SMC, DMC, which is weight, epoxy and silicons, and rubber. Thermoset elastomers, what we typically use, are polychloroprene rubber, which is commonly known as neoprene rubber. Nitrile rubber. Neoprene rubber is flame retardant, inherently flame retardant, like how PPS is inherently flame retardant. Whereas nitrile rubber is not, but then nitrile rubber is cheaper. Nowadays, there is a focus of going towards nitrile rubber because of the cost aspect. Silicon rubber and fluorocarbon rubbers, which is commonly known as Viton, that is the name of the bond. Okay. Insulating materials, when we consider, if I have to take a now case, this is a classic case where there was a earlier metal pin what we were using. This is MCCB release. This is how it looks from front, and this is the rear view. This is the inside view. This is the triplet, and in order to mount that triplet, we were using earlier metal pin. But then during the arcing, in the MCCB, which is not taking place in this release, but then because of the metal, the arcing was getting attracted towards this metal pin. This was of mild steel, and in order to prevent that, earlier the Teflon coating was done. So why to do all those things? So we have converted that into 40% glass-filled PPS material, which is inherently flame retardant and non-corroding and obviously non-conducting. Considering the heat resistance in this region, and other aspects that what we have discussed, this is the base material and it is working smoothly. After introducing this, we have forgotten about any of the customer complaints and those kind of issues. So material has got excellent dimensional stability, excellent chemical resistance, molding point of view, how precisely you can mold it, and obviously moment it is now thermoplastic, recyclability and compliance with ROHS and REACH is intact. So this is the advantage that one can get. Another case is, now I'm going to discuss certain forms of spring. Moment we say spring, typically people think about the helical spring only, but that is not the case. We will be discussing different types of compression spring. This is basically a polyether spring with 10 to 30%, 10%, 20%, 30% glass reinforcement, also with 30% carbon fiber polyether, and it is obviously non-conducting and inherently V0 being polyether inherently FR and non-corroding. You can use it in the application at 170 degrees centigrade. Again, just because if you use metal pin, a metal spring, it will attract the arc. Another case is the compressive spring, which is basically for restoring or repositioning the plate back in the stored energy mechanism. Okay, so this spring can get compressed. This is basically a cylindrical spring of polyurethane material with 60 to 70 hardness. There is a range in which this is available, and then it can get compressed up to 15% to 40% of the original size of the spring. And moment the load is released, it comes back to its original position. So compression set, that is the dimension by which it can recover, is about 5 to 8%, which is pretty good, as far as restoring the dimension, original dimension is concerned. And again, there are certain advantages. From the product perspective, we have to ask the question, what is the functional requirement of the component, and based on that, one has to select the material. Another case, now this is a patented product along with the patented spring also. If somebody says it is very difficult to visualize that this as a spring, for various product sizes, small rating to high rating, different things. I have captured only 3 here. So this is basically a changeover switch. Okay, changeover switch can be mounted horizontally as well as vertically. Now this from outside it looks like this is the handle, and moment you rotate by handle, there is a handle. Actually, this is the rod for mounting the handle. Moment you rotate, the inside there is a bridge which is supposed to move left and right, and in the neutral position and making on and off position. Okay. Now, if it is mounted vertically, the bridge, because of its weight and with the metal contacts, that is copper and all, it will fall down. So it will create always either off or on position. So in order to prevent that, we have used, or the product designer has designed a spring. Basically, this is that spring which you can see in blue color. Now the beauty of this material is this is actually covered within the housing and bridge cross section. Earlier, we have actually designed with thermoset, considering the arc aspect and all. But then, considering the lower cycle time, that is productivity from the thermoplastic aspect, lower cost, faster production rate, recyclability, we have considered or introduced now with thermoplastic polyurethane, which is working very fine. So what are the aspects that we have considered? High pressure and superior load bearing capacity, excellent flex life, high abrasion resistance, high cut or tear resistance. That is very important because bridge material is thermoset SMC with 30% glass reinforcement. So it will abrade the material like anything. Oil resistance or grease resistance. There are contact grease is also used. So all those aspects, excellent noise abatement, and vibration dampening. So all those aspects we have to consider while selecting a material or even designing the component. Now we are coming from another case where if I have to convert a thermoset to thermoplastic. Now why we use a thermoset material? Typically, people use thermoset material for two things main. One is the cost; they are cheaper, much cheaper compared to thermoplastics. Equivalent grades I'm talking about. And another, now we are coming from in our products is no melt deformation criteria, because thermoplastic material, moment it touches the softening temperature, it will start distorting. Moment it touches the melting point, it will start flowing. Okay, whereas in case of thermoset material, it will burn, but it will not melt deform. Now, if I need to have those kind of criteria and still get the advantage of thermoplastic, because moment we go for thermoset material, there are inherently certain issues. Okay, whereas in case shelf life of the material, there will be flash, because flash indicates the healthy filling of the cavity. However, that secondary operation of deflashing is a problem. Okay, and all that thing add the cost also. So if I use if I get a thermoplastic material, which after certain treatment becomes it will not melt deform, then that can be a win-win situation. So there is an option available now. That option is available from Eurostar as well as formulated polymer, and that is basically a radiation cross-linkable material. So this material is not as normal material. Let's say, for example, the crate, this what example I am showing here is 25% glass filled FR nylon 66. Okay, so you mold it, it will be a normal thermoplastic material. In fact, if you can crush the runners, you can make use of it again also. And after that, we have to give the exposure of gamma radiation, which I'll be showing in the next slide. And once the radiation is given, it becomes now, it governs the thermoset characteristics. Now, if you see, if I actually, the flame is applied to all these three components. Now, if you see the same material, that is 25% glass filled FR nylon 66, without radiation cross-linking, the component has molten, burnt, and completely collapsed. Okay. Whereas if the melting point of nylon 66 is about 260 degrees centigrade, if you go for PPA, the melting point is about 320 degrees centigrade. The same reinforcement, I have applied the flame, and if you see, it has also burnt and deformed, not as bad as maybe nylon 66, but it has deformed to some extent. However, if you see the cross-linkable material, it has burnt. However, it has not changed its shape. This is what we want, because if there is a flame hazard from outside or within the product, the functioning of the product should not be compromised. The tripping mechanism. Because all these equipments basically they are fuses. They are supposed to do their job and die. That is okay. One can replace that. But it should. They are protected devices, and they should not lead rise to damage to the further motor or other electrical instruments to which they are connected. If I have to show you quickly, these are the components which goes into the cartons, and it passes through the cobalt 60 cell. That is one of the method of radiation cross-linking. And after a particular dosage, this is the inner view of that radiation plot. It passes through that, and this is the section. This is orange is the cobalt 60 cell, and the radiation makes the activation of the cross-linking agent, which is in the silent mode in the material, and then it blocks the chain, and that is how the material doesn't melt deform. Now, if you see here, left side, if you see, there is a hot pin penetration test what we carry out. If you apply, because what we typically do, we increase the temperature 90 degree above the former melting point. So if nylon 666 is having 260, 260 plus 90 is 350 degrees centigrade, we actually apply that temperature and see the pin has gone through and through. Okay. And you can see even the glow wire also, it has, completely squeezed out the material, because it is much more than the melting point. And we do it within a fraction of a second, it happens. It doesn't have to apply much time. And if you see here, cross-linkable, it has only given the white stain. Okay, here also, if you see glow wire, it is only a stain mark. You can't see any other effect as far as melt deformation is concerned, Okay. So this can be treated as an alternate to thermoset composite if you can go in a right manner. It is basically for boosting the short-term high heat resistance while keeping the same injection molding process. That means your all thermoplastic mold will remain same. You can take advantage of all the thermoplastic design features, which is not practically feasible with thermoset material. FRV0 glow wire 960, it is compatible. It is a good balance between mechanical and electrical properties. The only disadvantage what I can see is the higher cost, because certain other advantage, that is WEEE ROHS compliance, a good surface appearance, as being it is thermoplastic, the surface appearance is excellent. Design freedom versus thermoset is basically you can design thin wall moldings, you can have click fit sections, even you can do ultrasonic welding before radiation. So all those advantages, whatever product designer feel like adopting, he can do it, and later on do the cross linking. So faster cycle time and colorable, laser markable with lower weight versus thermoset. Thermoset materials density is high, the weight is also very high.
Prashant,
This is another actually.
Prashant, we are running a bit short on time, so.
Okay, I'll go fast. This is the coil former. If I have to share with you, a normal coil former. Moment there is an interturn short. This is basically electrical abusive test what we carry out. This material, because of the enamel copper wire pressure, it has molten and it sticks to the magnet, moving magnet, and fixed magnet, and the entire assembly has to be thrown. You have to throw the entire contactor. Whereas these coils are replaceable, and customer look forward for replacing the coil and use the same contactor. After cross-linking, if you carry out the test, you can see there is absolutely, though the coil is burnt, but there is no melt deformation. These are the different components that we have gone for the cross-linkable material. This is the thermoset contactor breach. This is actually the breach, and you can see the flash, which is the excess material, which one has to remove. Thermoset material having a chemical reaction taking place inside the mold. Sometimes it sticks to the mold, and the part coming out will show you a short molding kind of feel, So this is another contactor breach, which we have converted from thermoset to radiation cross-linkable thermoplastic material. This is the contactor. Again, another rating of the contactor. You can see after the short circuit condition, the breach has burned. Okay, but this is thermoset, this is thermoplastic, but it has not melt deformed, because if it melt deforms, it will cramp the entire contact assembly, which is not desirable. Okay, modified thermoset composite, another case with polyurethane with certain combinations. We wanted to have continuous use temperature 120, CTI 1000 volts, arc resistance above 120 seconds, breakdown voltage, and so on. So all those properties, based on that we decide. Now the beauty of this component is there are 4 different copper terminals, though they look like on the same plane, but inside they are not. They are up and down. Okay, and during assembly, you cannot assume that they will be aligned with respect to the MCCBs which are mounted here. So even some level of flexing comes, it should not be cracking. So all those advantage considerations, based on that, one has to decide the product design, and obviously the material selection will be based on that. Okay, moment you go for modified thermoset composite, this is basically a modular design where we have gone for glass fabric SMC material. Okay, whereby the fabric based material gives the longest length of the glass fiber and orientation also to the desired direction, and hence it gives at least 100% higher mechanical strength compared to the traditional material. Nowadays, why I'm mentioning it here, because nowadays even thermoplastic fabric based materials are available, and there is a hybrid molding technology where one can use fabric based material and combination of radiation cross linkable material, and you can actually convert thermoplastic material to thermoset material to thermoplastics, and you can reduce the size because these give exceptionally high strength. If I have to go this component with a traditional form, the size of the product will go up enormously high. Okay, then functional requirement, different functional requirement, what we consider is based on the mechanical properties, electrical properties, physical flammability characteristics, and thermal properties. That all of us are considering all those things. And this is the modular design. You can see a single cassette in the MCCB where the entire housing is same, which will be supporting all RYB poles, different poles. If this is the these are those small cassettes which are mounted. However, the housing is of same thermoset material. Okay, this is the closed MCCB. Now, if I have to go for complete modular design, now this is the entire cassette. Okay, the big cassette. Now that is covered with a very thin component with the thickness of about 1 mm, and only some small parts are of outer parts are which takes less abuse and calls for less lower mechanical strength. All those things design by design you can convert all those properties. Okay, another case, electrically conductive polymers. Basically, this is the material which is nylon 6 with copper fibers into that, and with tin as the filler element, because then finally copper fibers to get connected with the conductive material, and you can actually inject that into a path, which is already having a recess into a thermoplastic material, and you can have a resistor, or you can have small electronic circuit with a cell which will give you the products like this. Okay, you can have these kind of moldings. Now this is that black part you are seeing. This is that conductive polymer which you can inject. You can do it with hot runner mold design concept, and you can feel this is also the path which is a conductive polymer. Okay, whereas this is the metal part. Okay,
Prashant, we'll have
fine.
To be a little bit fast.
That's fine. So this is the actually sectional view. This is another case whereby this is polycarbonate used with thermoplastic elastomer. Wherever there is a push button kind of requirement, there is a hole below, and you can press, and as there is no support for polycarbonate below, you have actually eliminated additional components. You can do by that also, and basically you can have IP protection also, which is very important criteria all these electric products. This is the contactor, another classic case. Entire housing can be of FR by IEC standard requirement moment it is having a live terminal. So instead of having the entire component into FR, we have introduced a small component which is having a live terminal into FR and lower 960 and CTI and whatever requirements, and the rest of the material is now non-FR. Okay, this is how one can use its skill, designer skill. Another classic case whereby this is the contactor what we are manufacturing. There is not a single hardware to assemble it. Okay, all those click fit applications, whatever this hardware what you are seeing, those are basically for live termination. Okay, this is another case whereby you can use thermoplastic material for actually burning, which is used as an ablative material. Okay, of course, this is FR material and burning in controlled condition so that it quenches the arc. Alignment feature, I will go quickly. Alignment feature. Alignment feature, this is the ACB isolating contact, SIC bridge, what we call secondary isolating bridge. This is actually fixed into the switchboard panel, and this is mounted onto the air circuit breaker, which goes and aligns. Okay, if you see these, finally they are getting divided into small aspects, single aspect, and when you convert into the block, it is a single block. Then all those blocks are separately mounted into the entire breech. Okay, this is the fixed part again into the secondary assembly kind of condition, and then when you assemble it in totality, you will find a complete breech kind of structure. Okay, contactor assembly, you can see here. There is absolutely no hardware which is used. Whatever metal part what you see here, they are actually for live conductive parts. Even rubber pad which is mounted below the magnet is also anchored within the material itself. This is another case, assembly feature whereby wrong assembly should be prevented by certain design feature. Another component, that is air circuit breaker, which I have shown for that SIC bridge. The single component has got multiple requirements. It should flex in certain area for click fit area, assembling the other accessories onto that. At the same time, it should be very rigid and other functional requirements. So the component designer and material selection becomes very critical for such kind of requirement. But then one single component, if you see this gray color, this is the single component on which various things are mounted for various functional requirements. This is the total assembly onto the air circuit breaker. Electromagnetic function for coil former, that is another criteria what we do. And product aesthetics, in finally, if I have to talk about, color, texture and transparency is very important. This is cannot be compromised. Form of the material, you see the earlier contactors and now the new range of contactor. This is you can clearly get a feel, whatever you see, you feel like using it or buying it kind of thing, even contour. Now the important thing is that one single material, if you mold, this is the single chip with glossy finish, semi-gloss, matte, semi-matte and matte. Now if it is molded in the single material with the single machine, single time, but then appearance is different. So one has to also understand what are you comparing, what is the base. I'm not talking about source of light, that is the different story altogether, but I'm talking about the mold finish, that is also equally important. Now these are the other texture, where we can use texture, and this is the latest range of contactor from the aesthetics point of view. These are the energy meter where you can take advantage of the transparency. You can have the matte finish to hide certain things. This is that same changeover for spring what we have discussed. Okay, this is with the handle. These are the new contactors. Okay, with accessories. This is earlier version of MCCB, then next version of MCCB, and air circuit breaker, earlier version, latest version with electronic features added to that. This is again air circuit breaker with certain additional frames. These are the switches. That's it. Thank you very much for patiently listening to me.
Thank you very much, Prashant. Very
Sorry, I have taken
valuable
additional
insights.
time.
I think all the people have been patiently listening, and they found it very valuable. Discussed in toto regarding the insulating materials, gave a brief insight on the types of materials along with the functionality requirements. So I think product applications as well as aesthetics are important now as we move forward. You gave us some very good examples in terms of MCCB, the thermal magnetic release you talked about, then composite springs in new materials or the latest trends as far as materials are concerned. Then you gave us a very good example in terms of thermoset and a conversion to TPU for an application where recyclability has also been taken into consideration. So cross-linked polymers, I think that's one of our favorites. So definitely, I think as we move forward, it'll be a growing market. And I think LXE would be very much interested that the market grows substantially for cross-linked polymers. So thank you very much. And you also discussed on the electrical conductive materials. So I think that's also a new area which has been growing over the last few years, part integration, smaller components. So thank you very much, Mr. Prashant Viragi. We enjoyed and thoroughly it was a learning experience for us.
Thanks, Rashmi. And one point I wanted to mention is that Alexi and Satish, their presentation were too good. Rather, having given a choice, I would like to have listen Alexi in 1:1, once he visit our company.
Yeah, definitely.
It
We'll
was so
plan
good.
that
It was
out.
so good.
Alexi, you have to say that, although we have a couple of slides for you also.
Alexi, apply for the visa.
You're mute, Alexi.
Oh, sorry. Yeah, of course. But I think time is flying by, so I won't take so much time, let's say, and maybe just after this very nice presentation, just say a word that to make all this data is important, and maybe to make the link with the next presentation. We at FPL Eurostar has some workflow data of some grades which are really there to build the design, let's say.
Okay.
Okay, so thank you very much, Pradeep. I'd request you to share your screen and start. Actually, we should have more time with both of you. I think wonderful.
Thank you.
Should have started as 2 slots instead of 1 on the same day. It's okay. We can go ahead. We can do the extra hours, no problem.
Sekar's
Okay,
voice
so-
is very low. Sekar, we are unable to hear. Rest of the people we can hear, but I am unable to hear you.
It's true. I think no, I just said that maybe we could have had it as a 2-part instead of 1 part today. Trying to have.
Doesn't matter. Doesn't matter. Okay.
We'll go ahead. Yeah.
Yeah.
Maybe a little extended hours, no problem.
Fine.
Thanks, Pradeep. I think you can start.
Okay, am I audible?
Yes, yes.
You
Okay,
have to
so
be a bit
welcome,
closer to the mic.
all attendees. Again, good morning, good evening, good afternoon, which part of the world you are. So coming straight to the topic of today, which is product design optimization, specifically for FR compounds. I would like to begin briefly by touching upon the product design process itself, how we do it now and how it is sort of evolving with the disruption in newer technologies that have come in. Now, typically, if you look at the way we go about doing design, it begins with a need assessment, all sorts of research, market research, product research, technology research, and ideation process is kicked off to generate concepts. They can be sketches, layouts, reference material, markups, all sorts of techniques are used to make these concepts and ideas. But essentially, what is it that we do at this stage is to evolve a few selected concepts that we think meet our need, perceived need or the market need. Essentially, there are 2 kinds of needs: inside out, which is usually technology driven, where we have a new process or new technology, and then we want to push that into a product form into the marketplace. Or they are outside in, where market trends, customer mapping, new methods, or basically we want to give a better value proposition and new concepts are generated. So when this process happens, even when I would say, when the bigger design studios are involved, there is a sort of a handover issue. I use the word handover issue because design is done, concept is in place in terms of what we like, but the late stage processes have not been considered yet. And that basically means life cycle considerations, feasibility of the concept that has been made, material aspects, the manufacturability aspects, the environmental impact considerations, all that is not done. And this I've seen as an issue even with the big design houses. There's always a sort of a disconnect, some sort of a disconnect always comes. And this is where I think the new techniques and new model-based design definition is helping in a big way, where the design is really converted into an accurate model-based design definition, which is more structured. The model is a representative of the part's features and functions in a virtual manner. It is geometry as the part is intending to be having. It has to have drafts, it has to have material properties, it has to have representative volume similar to as what the part will have. It'll have that sort of boundary conditions, even sometimes depending on the environment in which the model is being developed, it can also have a certain operating environment. So the benefit of doing this in terms of converting that design to a model-based definition is so that we can simulate, and which is the really focus of benefiting from simulation techniques in design of FR materials for this. So it starts all the way from a sort of product data management, digital markup, virtual reality, CAD, FEA, augmented reality, CAM. Everything revolves then around this model. As the project progresses, all the way from basic idea to product engineering, the common building block, which is the model, is being referred to. So the accuracy of the model and the intent of that model has to be extremely good. So I'll touch upon this in a little detail, particularly from viewpoint of E&E industry. When we're using FR plastics, we can do validation, which can even go to clearance and pre-page validation at the design stage. We can go to electromagnetics, which can go to, of course, the standard evaluations of ensuring part fills well, moldability, manufacturability, but also in terms of assembly, doing stress and thermal checks, etc. So this entire gamut of even the development that is required in the electrotechnical industry is then centered around the model-based definition. Simulation is very common. I just want to touch upon that. Today the fact is that the entire automobiles, airplanes, jet engines are being made multi-locational. There is global supply chain. The design teams are spread all over the world. There are design standards that we need to adhere to, and a lot of virtual mapping of these processes, techniques, test methods, prototyping methods is actually getting converted to simulations. And that actually has changed or sort of redefined the design process itself. A complete shift from the traditional design process is happening, where starting all the way from the selected concept model, when it's converted to a model, the iterative loops are happening virtually at the design desk itself. Of course, you need the domain knowledge and you need the experience, and we need to know exactly what we are looking for in terms of standards or the virtual tests that need to be done. But prototyping is getting virtual, the thermal checks are getting virtual, the mechanical checks are getting virtual, the drop tests are getting virtual, electromagnetics is getting virtual. It's really virtual functional prototyping happening right on the design desk. So in that sense, the design model itself has evolved and changed. The way I see it now is that in the old days, we used to say, oh, good part is a combination of a good material choice, a good tooling, a good processing, proper tooling construction, good design. But I think now it is also true even now, except that the process has now become a good part is a combination of a good part design and good production. where the good part design has sort of evolved to encompass all the other things which are late stage processes which are getting incorporated right at the design stage. So in that sense, the product design has come right in the center. I want to touch upon this again because all the way from user needs and ergonomics to looking at our production planning process and even I would say manufacturability, tooling, additional SPM required or whatever revolves around our consolidated model-based definition that evolves from the product design today. So I'm going to take an example to walk you through this experience using a sensor. It's a current sensor. And this one is for particularly very high accuracy. It's used in the electrical industry, in EVs, HEVs, and there is there are various types. The main idea is to sense the accuracy of the current or voltage, in this case current, in as accurate way as possible. And when we are dealing with 2000 amps or 1000 amps, and so there's a lot of sensors and technology going in there, various kinds of coils sensing this, which eventually translate back into measurement of the current in an accurate way. There are variations depending on the thermal profile. Some current sensors have heat sinks to dissipate heat and to protect electronics. The one that has been taken as a case for this presentation starts with the concept, and a design was done. I will not get into the details of that, but show you what the concept looked like. So a current sensor was developed here, and it met all criteria. Heat sink was designed to extract the heat out, where the PCB board was on the underneath of the heat sink with the MOSFETs reaching temperatures almost up to 178 degrees. But the housing had to be not in contact with that temperature. It was a heat sink, and the housing was coming to approximately 120, 121 internal heat in passive situation. So we're not talking about the outside, we're talking about the inside. So in this case, we met all the requirements and the product was developed meeting clients' expectations, or so we thought. The challenges here were plenty in terms of material selection, V0 rated, which exact grade for that temperature, for the dimensional stability we needed. Accordingly, the PCB sizing and assembly had to be built. Heatsink also had to be sized based on thermal profile of other components, internal components, assembly, tolerance, clearance, determination for accuracy, maintaining that calibration and accuracy even during the assembly and production stages, and of course, to keep in mind the secondary operations. In terms of plastic design optimization, in addition to material choices, the accuracy part, which has linked to dimensional stability, had to be ensured throughout the process, and fastener sizing had to be done. The loading had to be not too much, and also the product had to be designed that once it goes through its operating environment and changes in that, the consistency should be maintained in the performance of the sensor. So various ideas in terms of heatsink and housing combinations were developed in order to meet the steady state thermal requirements. And these are just some options that you see of the heatsink with the housing that was chosen for all the functions that I described. And then we entered, of course, the concept validation stage with the model-based definition, models being ready. These are production quality models, fully drafted, and in all aspects, all assembly, clearance, tolerance have been taken into account. A lot of tests were done to optimize the profiling, spacing of heat generating sources, a number of fins, width, length, height, everything, all that was done. And on these concepts, finally, one concept was chosen which gave the best heat dissipation and the lowest profile of temperature along the outer edges, which was extremely suitable for the plastic housing. And the design was done, or so we thought. It was time for us to get the raw material supplier and the tool maker in the game and look at the simulation results from viewpoint of moldability. The FR V0 material was chosen, proposal looked like, I mean, we got the project in the bag. Then came some results. With this semi-crystalline material, even with very balanced center fed gating, we got extremely high warpage. Deformation came, and the variation of that deformation was a bigger issue because on some corners, the fiber orientations, and on the other corners, the fiber orientations, and due to volumetric shrinkage, one could see that this deformation is going to have a different effect on different areas of the part. Tried with a couple of different materials, but we could not contain the deformation to less than 0.8 in the direction of our assembly, which was a huge concern for a part that required extremely high dimensional accuracy at the time of assembly. So we looked at a way to contain this deformation because we didn't want to give up on this product design, is to use the fasteners. There were 4 fastening locations on this part, and we mapped this deformation back in the stress analysis program to look at fastener sizing and to look at the stress levels that we will get for the same deformation that we could try and match when the final product assembly is made with the fasteners in place. But unfortunately, though you see here 8-9 megapascals of von Mises stress is manageable for the housing, but it was not acceptable for the loading the fasteners were required to do, the force, the fastening force. So for this kind of a product, we did not need a very high fastening force. And the project simply was, looking like not going further. Further, we got, sink marks in certain areas going up to 100, 120 microns with this material. So a lot of red flags were raised with the design analysis. Warpage levels were not acceptable. Stresses were not acceptable, fastener sizing wise. And then after the discussion with the tool maker and the raw material supplier, we decided to use an amorphous material with a higher thermal profile, but with V0 properties, of course. The idea was, can we get better accuracy and reduce the holding force? So the plan ahead was pick this material into simulation, look at the heat sink also, because somehow we got the thermal profile of this material was a little lower than the thermal profile of the semi-crystalline material. So what could we do with the heat sink to reduce the thermal dissipation further? And this was the sort of scope that was decided for the second stage. So again, we are iterating on the design desk. There are no real capital investments made yet. There is actually, the concept has not left the design even into the prototyping yet. So a new study was done with a different material, and we got fantastic results. Fantastic because even though we have a warpage in the assembly direction of about 0.4, but it's extremely uniform if you see along the edges. So it sort of neutralizes in terms of within tolerances. The net effect of warpage that we saw was just barely about 100 microns, which was extremely comfortable with the fasteners to assemble flawlessly. So as you can see, the distribution is extremely even with the balanced gating, and this became a non-issue with the change of material. Also, the sink marks, if you look at the cyan region, they dropped from about 100, 120 microns to just about 500 microns, 50 microns. So that was a major improvement as well. And then we also did other evaluations. I mean, like this is basically, you can see surface flatness. I'm talking about the face here of the part, because though this part was going to be textured, but this entire face had to be absolutely flat. So was the construction inside. And the flatness in the part, if we look at the regions and map them on the scale, was within 50 to 100 microns. So extremely good flatness as well. So then the challenge was to redesign the heat sink, and we could not get the lower thermal profile on the heat sink was already optimized. So we used the housing to reduce the rounding on the sides and to create extra space for the heat sink, if you can see my mouse. So we managed to get about 20% more area on the housing opening for the heat extraction. So we were able to resize the heat sink doing that and drop the temperature down to 92 degrees, which was extremely comfortable for the new material. And so we proceeded with the project from the design desk. First trials from the tool, review of the lab test with perfect results achieved, project closed. So I want to talk with this example, the benefit of the simulation, because it has a huge benefit in the E&E industry. Simulation models offer a lot of flexibility. What I've seen in my experience, say, for example, when we are doing design and we are doing stack up of clearances and tolerances, and we want to look at the assembly functions, we want to look at the model interaction, part interactions, we want to look at the dynamics, we want to look at load transfers, we want to look at other effects. So many times when we do this level of virtual prototyping, say, for example, I have a model, I'm doing all this, I cut through a section, it's a virtual slice, I can see the effects right through the section, right through the thickness of the material, which is impossible to do in real life. I can't even put a sensor there. So it's not just replacing or kind of as an alternative to real life tests or development. It's giving absolutely new dimensions or avenues. I've seen some cases where parts had to be evaluated at certain temperature where we don't have the real life facility to make that operating environment with those low temperatures or those high temperatures, but in simulation we can do that. So there are tons of advantages in simulation of various kinds, but you need to have a lot of expertise on the design desk to do that. I want to give you some examples. For aesthetics, for a product designer, surface quality is extremely important. Of course, do structural analysis, all kinds of fatigue, thermal, vibration, even based analysis. Something happens after a while, then what is the effect, etc. And of course, CFD, electromagnetics, HVAC, etc. Specific for plastics, drafting all the way checks core cavity extraction, viability, part material filling. Am I going to get short shots? Am I going to get air traps? Am I going to get well lines? I can do machine sizing. If I have a certain equipment, I can actually design my part to be processed in that equipment. I can balance all that. I can do my cavity layout of multiple parts and do run balancing in such a way that I maximize productivity. So all this is possible straight at the design desk. And of course, there are lots of other analysis that we can do. I just want to throw you some examples from other areas which are also relevant in E&E. I mean, you'll say, what has car to do with E&E? I'll tell you. So CFD is a very common tool which is used in design of automobiles. You would have seen all kinds of fancy cars, race cars, driving this technology, rockets, even military equipment and whatnot. Here you see an example, a very simple example of a car. I think it's VW ID3, where CFD was coupled along with clay models for the wind tunnel tests. But the way the coupling was done was not only to reduce the times of development, but also to make extremely lower investments, because you could do the test with the scale models, which were representative of the model-based design definition. And the changes and the optimization of aerodynamic profile was all happening virtually, and this process kind of cut the cost and time down in a very big way. Same thing you see in trains these days, whether it's high-speed trains or magno rails. Huge contribution is being made with the CFD techniques. We are talking of trains that are developed for 300 miles an hour. Here you see an example from the concept to the reality on the right. All these are real life development examples. So what has CFD to do with ENE? It has to do with the conjugate heat transfer. As the products are getting miniaturized, high frequency products are coming in, the thermal profile is going higher. So there's a lot of pressure on reducing heat. It's usually done by heat sinks, forced air cooling, but it's also done by laying out the components, inlets, outlets, setting up that domain where the extremely high heat generating and highly miniaturized electrotechnical solutions are also possible with reliable working ranges by balancing heat extraction by using CFD. So this is the same techniques as used in the design of automobiles, but for a different purpose altogether for the ENE sector. Here you see another example of an EV charger. This was done by me last year for a European client. Here we used these techniques extensively to get a lot of high wattage development in a very short time of development, as well as in a very compact form of the charging solution. This is also a technique used in data centers. So basically, you have thousands of computer chips and heat sources generating heat that needs to be extracted, basically in all the areas where there's user comfort at stake, even in hospitals. So this has extremely vast application range. Of course, hydrodynamics. I just want to give you one example from plastics as well, since we are talking about plastics. Everybody knows about this model of development, but I just want to give you one example of something very unobvious, very simple analysis of shifting gate and well line for aesthetics. Now, this is an example where this is an automotive part. The red region, what you see over here, is not the place where a well line is required. Is not the place where a gate mark is required. Is not the place where any flow mark is required. And these places have been demarcated because they are seen by the user. It's a sort of a bezel which will carry instrument cluster inside. And with the way the planning was done by the tier 1, it was always getting some sort of a mark, some sort of a well line. And even though a lot of variations were done, but
can I break in? We are like actually running out of time.
Yeah, I have 2 more minutes. I'm done.
Okay, sure. Thanks.
And so we just looked at a different gate location, in this case from the side. This was, of course, after a certain design of experiments, and you can see the progression, and the well line was relocated on the side. But the good thing was it was a planned decision, and as you can see, the well line was located where there was a structural area and not the visible area. That area was getting covered by an overlay part. So eventually the visible area of the bezel became absolutely flawless. So I want to conclude now. I just want to say one thing in the end. A lot of this is happening, this revolution, which is coming on the desktop of the designer to look ahead. But of course, a lot of knowledge and expertise is required. Various experts sometimes get involved. But also what is important is this design thinking and solution building is coupled with the organizational management's objectives and goals. Because even if you're going to set up a new shop floor or you want to launch a product in the marketplace, the same common design building block, the design model, can be used. It can be used for furthering technology, launching new generation or evaluating new generation products, and it can be used for even things like IPR or marketplace studies or virtual presentation of a product that has not even launched yet, for say for crowdfunding, for example. So it's very inherent and moves together, and then this process has huge benefits. Thank you all for listening.
Yeah, thanks a lot, Pradeep. Thank you very much. I think we should have given more time to both the presenters. Wonderful presentations. I think Pradeep covered up right from concept generation to the design simulation, development, validation testing. And I think product life cycle has become more and more important as we move forward. So feasibility of the concept and actually taking it to the field, making it work. I think the entire with examples have been covered up superbly. Thanks, Pradeep. A wonderful presentation. And I think although we take into consideration some critical success factors, but part design has become more and more important as we move forward, and simulation has become critical, especially for aerospace, railways, the way you gave the examples on. So moving forward, I think these areas are the next gen requirements, and they will definitely get integrated into the system. So what Prashant talked about was miniaturization and the aspects in terms of designing electronic components, vis-a-vis taking into consideration the heat generation, which was covered by Pradeep. So I think both have covered up the design aspects very beautifully. I would now just share my screen. Yeah, Alexi is there.
Yes, of course I'm there. I'm there.
Yeah.
But
I
maybe
knew you
Rashmi,
couldn't miss this.
but maybe if possibly, I will ask you to share a screen because otherwise it will be too long.
Yeah, I am actually sharing your screen.
Yeah.
Can you see it?
Yes, I see it, but I won't comment it too much because what Pradeep mentioned, he's so much more up to date than what I know about mode flow simulation and things. But maybe those let's say those pages are no more up to date. Let's say what I learned already was really impressive. But everything, as explained by Pradeep, is based on data. And the thing is that we have to generate the data. In some cases, it's a bit a limiting factor for us. Let's say, here you see an example on a conductive material we made on mode flow experience. It's a tremendous nice tool, an incredibly nice tool, but up to let's say our experience, the challenges were always the surface aspect of the part, because, and especially with flame retardant, sometimes the shear is high enough to, let's say, to damage our flame retardant, and then you have streak marks on the surface. So up to my knowledge, it was not possible, but with what I saw today just presented, I'm not sure it's still up to date. Okay, so maybe next page.
Yeah.
I'm trying to go fast because, of course, we are running out of time. But
yeah, we are actually run out of time now.
Yeah. Just to explain that generating a UDB file, meaning a file to characterize material, is not a piece of cake. It's really a big work, because all the viscosity, thermal, mechanical properties has to be tested. And so we have some, but in each case, unfortunately for us as a compounder, we cannot have it for all product. But let's say when we have the data, the experience is that it correlates very, very well to the reality. But once more, I won't go into details, but each time when we generate a UDB file.
Hello.
He's not audible.
Yeah, I think.
Regarding data we already have, we have already within FPL and Eurostar a nice range of products. Maybe you can go to the next page, Rashmi.
Yeah.
But it really we can map, let's say, the reality at least for polymer 6 and 6.6 from low amount of glass fiber, meaning 20%, to high amount of glass fiber, meaning 97% with 6.6 and copolymer. And it's really an asset, and those value, let's say, have proven on the market to be, let's say, very reliable. Otherwise, I say yes, the single limitation we see, or the single feedback we have, is sometimes surface defects cannot be predicted. And this is maybe not true, because it seems it made so tremendous progress, but sometimes really the weakness I would like to point out is I don't know to which extent it is possible in software, but the shear on the material really has to be measured or estimated, and the correlation between a too much high shear and, let's say, a surface defect is not as obvious as a decrease in viscosity. So from time to time, we still have some surface defects in flame retardant grade, but to me cannot be explained really by simulation. But maybe Pradeep will say the contrary, because he's much more up to date than I am on those ones. Okay.
Yeah, thanks, Alexi. There's no sound. Hello?
Yeah, we can hear you, Rashmi, but
Hi, how are you, Gils?
hey. Good to see you.
We are not able to hear you clearly somehow. Alexi?
Yeah, I know. Maybe my computer is worn out. I have to change it, but okay, we can hear you. But let's say, single message I wanted to pass was really this limitation. But what a nice presentation today. Really, I learned so many things.
Okay, Rashmi, I think you can take over, and let's go into question and answer.
Yeah, I'll go to the question and answer, because I think there is a slight signal issue. We have a number of questions, so I'll quickly take them up. One was on how can simulation help in any product launch? Will it expedite the entire process, or can we use it for our new products, or how do we work on it? I think this is for you, Pradeep and Alexi.
Well, if I can share my view on this.
Yeah, sure.
See, when we are launching a product, the potential customer has to be shown the features of the product, has to be shown how it looks, how it functions, what will be its performance characteristics. And even sometimes that launch process these days has sort of changed, and we want to get in the funding, whether from management or do crowdfunding or go to a VC. And we want to bring investments. So all this with virtual development actually is a boon for people and entrepreneurs who want to plan product launches. First is, of course, reduction of time, but all this can be done virtually, and investments are being mobilized entirely with virtual proofs. So it helps in a very big way. It's like recently, I will not take the name of the product. In the US, I developed a product which was presented virtually to the VCs, and entire project funding was done, and not a single capital investment had been made in the product.
Yeah, okay. I think that should help in many ways. Alexei, you'd like to add on something?
No, really, I think I'm not, to be honest, I'm more specialist of material than specialist on simulation. And today I was just like a young child at school. I learned so much.
So I think it's like as we move forward, maybe the design concept, material concepts, the validation testing, I think the entire thing will have to be integrated together for us to take this forward. So I have another question, which is what are the typical simulations for electrical and electronics?
Oh, one has to start with the concept. I mean, take for example the switches. Even in the electrical and electronic industry, aesthetics is very important. Surface finishes are very important. Sometimes the products are painted, but the surface quality is extremely important. And with simulation, the data that is being sent out, the product that has been designed, it has a certain surface quality. Even in traditional prototyping methods, it's extremely difficult. But today, during designing, you can assess that surface quality. There are various tools in simulation. So at that stage itself, the value of visualization and simulating the environments in which it'll be used gets into use. So aesthetics is a very big area. Of course, you can use thermal tests. I just gave an example, but you can do one of the very important things in electrical is the clearance and creepage, meeting those requirements. So you can take your assembly full of electrical contacts, fully cabled, virtually assembled, with all circuitry in place, and you can actually do your clearance and creepage evaluations today. You can also do frequency optimizations. There are simulations available for that. Of course, at the basic level in the R&D, MATLAB is used, which is also a sort of a simulation. Then, of course, you have more advanced simulations which address the noise and the sound and all sorts of characteristics which are humming, which are there in the electrical and electronics industry. So there are various facets of simulation, and now you have multi-physics. So especially in the electrical appliances, the temperature changes, there's a lot of heat generated, and then the resistivity, conductivity, etc., they get affected. So you can do multi-physics simulation to look at those effects. So there are various kinds of simulation available.
Yeah, thanks, Pradeep. I think this one's for Mr. Vairagi. So how does a final product compare between cross-linked polyamide to thermosets? What is the thumb rule basically in terms of the cost ratio?
Basically, if you have to see the cost ratio, you cannot simply change the thermoset to thermoplastic blindly. Okay, say for example, typically traditionally drive shaft and contactor bridge, these are the elements which are carrying the live terminals, that is contacts basically, where the arcing takes place when the contacts are making or breaking. So such components are in the very close vicinity of the temperature, which will make it to vulnerable, that is from the temperature point of view and flame point of view. Such components, if you target, then yes, you can able to make the same component with a lower size compared to what typically thermoset materials are used. However, once you reduce that size, you can reduce the entire product size. So if you compare 1:1, I'm coming to the answer now directly. If you compare 1:1, you may not be able to say, because cost of the thermoset material versus cross-linked material is fourfolds. Okay, literally fourfolds effective cost of the component. So if you can get certain design features in the reduced form, then the entire product size will come down, and by there you can save it. Okay, so this is not in component in isolation. You have to see the complete cost of the entire assembly. Yes, sometimes, say for example, the one of the mini contactor breach, what we have replaced, actually, even we have used the same mold, thermoset mold, we have converted into thermoplastic by removing the cartridge bridges and passing the cooling water. So there, actually, we could save merely a very small amount, maybe a few lakhs rupees we can say. That was not the target. We wanted to overcome processing issues and production stoppages and all those issues. Have to remove the molding, all those things we could address. So, but then if you design a product in totality, yes, that makes a big difference. Sometimes, many times the reliability of the product is also important. Even if you can make use of the recycled material and somehow manage to control the cost with the same component size, you can control the customer complaints. Because bad name in the market will make you to lose the orders. So you have to see into the entire perspective, not again as a single component per se. But yes, one can do that by designing it appropriately, because component thickness come to 1/4 literally if you use cross-linkable material versus thermoset material for the comparable glass reinforcement.
Okay, thanks, Prashant. And have you tried making any electronic product using natural or dye coloring them to different colors? Will that be feasible? Like just a question someone has raised.
Yes, we can.
Okay, and have you tried it out on a commercial basis, or that's sort of difficult?
No, see, it depends, because many times, aesthetic point of view, once you make any product, you have to have, what do you say, consistency in the color, so anything, if you change, you have to ensure that one has to get the material in a larger quantity on a regular basis with the same shade. So typically, we rely upon the material supplied or a color consistency from the manufacturer, but yes, we sometimes we do use master batch and make such kind of things.
Okay, thanks. There is one like a lot of information floating around on 3D printing machines and customization using 3D printing. So how do you think it's feasible for the electronics industry?
We are actually, in fact, that is my one of the biggest dream in my organization to implement in the production level. In fact, we have started using in our energy meter, that is in our Mysore factory. We are using 3D printing machine for producing the component, but that is not really so mechanically important, But yes, we do use it. Basic limitation, what I see, but then whatever international electronic magazines, whatever I am going through, the glass fiber length and the orientation of the glass fiber in the component, that is making a limitation for, because layer by layer the material is being laid. So if that is the case, the bonding of that material is not as good as what we can get in terms of compaction by injection molding or even by extrusion. So presently the mechanical strength is a limitation, but then yes, I have seen certain composite with high glass reinforcement and giving a very good strength.
Okay,
It
so
can
there
reduce
is a
the
lot of
production time
improvement
very.
which has to be done.
Yes, so the biggest advantage of that is basically moment a new product is being designed. Many times, many iterations do come, but we have to take in consideration, because once the product evaluation starts, then many times changes. So at such times, or many times the quantity is also less. If you have to change the quickly, some customer wise, customer requirement point of view, today this is the product, so certain components you may keep constant or same, but then if you have to change quickly some aspects, then it is not worthwhile for making the tools for all that. Even another case, when we are making any product like say SAB or MCCB or contactor, it is not a single product, it is a range of entire frame up to say 0 to 100 ampere, 100 to 250 ampere, 250 to 500, 500, and so on. Not only that, in that also there are certain accessories which are which is a requirement from the customer. So there are actually hundreds of molds are required. So if quantity is less for certain accessories, it is worthwhile for relying on this rapid prototyping, kind of
Okay.
approach. So it is a good process, I would say, and I wish one day I can even make normal components using this process.
Sure.
That's my desire, I would
Okay,
say.
yeah, definitely. There is one more question. I think this is the last question I'm going to take because we've actually overshot the timings. This is on automotive. How can we confirm the cycle time through simulation or mold flow? Is that possible? I think this is for you, Pradeep.
Yeah, it's possible if you are looking at stages of injection molding, and you want to know the cycle time, then it is clearly defined in various stages of filling, packing, cooling, etc. But if to confirm the exact cycle time depends a lot on the part, on the way you designed your gates and runners, what is freezing first, which region is freezing first, which region is freezing in the end, the type of cooling system you have in the tool. But yes, if you are able to give adequate amount of data in the simulation software, you can get very accurate cycle times, to give a short answer.
Thanks, Pradeep. Thank you very much. This is another slide on polymides where we show our competency and our various grades which we have with us. We will have another series. Tentatively, it is scheduled for 18th of February, where we talk about the environmental impact, OHS REACH compliances. So that will be our next webinar. So once again, I'd like to thank you all. And thank you for joining. Although we overshot time, I think most of the people, participants are still with us. So I'd like to thank all the participants, all the panel members, and special thanks to our IT team, Venkatesh, then Sarvanan for helping us out to ensure that everything is on track and it's as per schedule, except for the timing part. Yeah, definitely. Thank you very much.
Thank you. Thanks.
Yeah, Alexi, Shekhar, would you like to add something?
Sure. I think even though we are overshot by 30 minutes, I think we require maybe as another show of this individually for both of them. Let us plan it again. Okay. Thank you very much, Mr. Pradeep and Mr. Prashant.
Thank you.
Thanks a lot.
Okay. Thank you very much. It was wonderful.
You're most welcome. Thank you.
Very learnable for us.
Yeah.
Thank you.
Thanks, Pradeep. Thanks, Prashant. Thanks, Alexi. Thanks, Shekhar. Thank you very much, all of you, for joining.
Pradeep, it was a nice
Thank you to all the
presentation.
participants. Thanks very much. And in case you have any queries, please feel free to come back to us. Our email ID is here. So for any information, you can contact on our mobile number or a WhatsApp number or email. We are all available, and we will also coordinate with Prashant or Pradeep in case there are any specific queries. So
surely, you're welcome.
Yeah, thank you very much. Thanks a lot, everyone.
Thank you. Bye-bye.
Bye.
Bye.